Well, I guess that I'm the first to get completely done, which is not bad. Is that correct?
Please allow for some at the end, some like opening ideas.
Well, in fact, this lecture altogether is about opening ideas. This is an ambitious plan. This is an ambitious plan. I hope I can go through. There will be not so many details, and compared to certainly the first two talks, there is much less analysis. There is much more an algorithmic approach and questions, a lot of questions that will come up. Okay, so I like to phrase these ideas of geometric problems in the context of shape differential calculus, which I'm going to describe quickly, and then there will be applications. So what do I mean by that? This is a classical field, going back to Adamar. It has been certainly cultivated mostly by the French school, Murat and Solesio, Sokolowski, and others. Let's say that we have a functional that depends on a domain, and perhaps on another object, a function or a vector of functions that depends on the domain. This may be the solution of a problem, of a PDE or a system. So altogether, this is a domain functional, and we want to minimize it. Well, this has a lot of applications. Certainly the questions of whether there is a minimum of this is a very difficult question that depends on the structure of the functional and so on. I will not be focusing on questions about existence or uniqueness. I will be focusing about computation, assuming that there is a solution. And I'll do it in the context of, let's say, gradient flows. The purpose of this is to tell you how to deform an initial configuration that might or might not be related to the final result, deform it in a way that we end up with an equilibrium, maybe a local minimum typically, or stationary point, not necessarily the global minimum. And that will be a geometric gradient flow. So we'll be going in a direction of descent in respect to the energy. In order to do that, if you remember the talk of today, the previous lecture that I gave, the gradient flow basically is an equation of the form derivative in time of a certain function is minus the gradient of a functional, perhaps the sub-differential in case the functional is not differentiable. So in order to introduce similar ideas in this geometric context, I had to sort of explain what this means, but most important at this point, explain what this means. What is this object that I'm going to be dealing with? The object is this capital J, and we need to talk about the differentiability of it with respect to the shape. That's why the name shape calculus. So imagine that you have a domain, okay? In this domain you have a vector field, V, that depends on x. You have a point x, and then you define, let's say this is a vector, initial condition equal to x, okay? So with this flow, given a velocity, assuming the velocity is, say, for instance, ellipsis, so that there is a unique solution of this flow, you can deform the domain. And that way, you can go from a domain, an initial domain, let's say omega naught, to a deformed domain, omega t, where t will be the time evolution. So imagine that this is slightly deformed. This is omega naught, and this is slightly deformed into omega t. Okay? So in order to define derivatives, we need to see what happens with small changes. So I'm introducing a small change now in the domain, and that induces a small change in the functional, which I'm going to call j of omega t. I subtract from the initial value divided by t, so I scale this difference, and I call this the shape derivative of the functional in the direction v. Of course, there is a question whether that exists, in what sense, and so on. So we'll be more specific with examples later. And since this functional may involve itself inside a function, which is a solution of a PDE, this y function that I mentioned before, you may remember solution of in general solution of a boundary value problem. This one here. The question is, what happens when you change the domain? Well, when you change the domain, in this new domain, you can have to imagine that you solve a different PDE, corresponding boundary conditions and so on, and the solution of that PDE, perhaps viewing the original domain through a transformation, so it's defined in the same domain, is this function. So composed with the transformation, now this is defined in the original domain, and I can relate it to the original solution, in the original domain, scale, and this is the material derivative. So we are just following the flow. It's a Lagrangian derivative. Okay, if you subtract from it the space dependence, typically what people do in continuum mechanics or fluid mechanics, this is the partial derivative in time, which in this context I'm going to call the shape derivative. Okay, and it has to do only with the formation of the domain and not with the flow, with the velocity. Okay, and for what I'm going to say next, there will be vectors, velocity vectors, that will be denoted with boldface, sometimes with an arrow, and this will be the normal component. Normal in the direction of the, by nu I will mean all the time the exterior normal, unit normal to the domain. And I'm going to say, if we are in 3 dimensions and we are dealing with the boundary of the domain, which will be a 2D surface, I'm going to call by this the sum of the principal curvatures, and I'll call it total curvature.
The material derivative is difficult for me. So y is a scalar function.
It may be a vector, but let's say it's a scalar.
And then you make the limit of the difference between y omega t
composed with a map. So this is now defined in the original domain.
Oh, I see. So
So you map it back. You see the function, which is a solution of this problem, defined in the original domain through the map x. Now these two functions are defined in the same domain, and you can see the change. Okay, you scale with t, and you call this a material derivative. Okay?
So y is a function of space or a function of volume?
Well, the function y is defined for each domain, let's say. Okay, so think of the solution of the Laplace equation with boundary conditions equal to 0 and with degree and forcing. Let's say the forcing is 1. So when you change the domain a little bit, you have a different function y because you change the domain. The function is a function of x. Then you map it back, and that way you define this object.
So a function is a function fixed in t.
Yeah.
Okay, thank you.
And these are very handy theorems, transport theorems, that are well known in continuum mechanics. So what happens when you differentiate an integral that depends on is defined on the bulk, on omega, and what happens when that integral is defined in gamma? And these are standard results. So let me just go through briefly. This is the best known. There are 2 components of the differentiation. This is what happens when you differentiate with respect to the integrand. Okay? But then you have an omega on the boundary, so that's the differentiation with respect to the integral, and you get an integral over the boundary of omega. When the function happens to be defined on the boundary, the formula is rather complicated, but again comes from differential geometry. You have the same structure when you differentiate with respect to the argument, the integrand, but rather more complicated expression when you differentiate with respect to the boundary itself. You see? You have the normal derivative and the mean curvature or total curvature with this notation appearing. Okay, so these are standard results that I want to use. So here are 3 examples just to illustrate. Imagine that J is just the volume of omega. Okay, so the function phi in our previous discussion is 1. Okay, this function here is 1. So when you differentiate, we get 0, because the derivative of 1 is 0, and then we get just that formula. Okay, so that's the derivative, the shape derivative of this, of the volume. You can do the same with the area. So now this lives on the boundary of omega, and the function phi is 1. So this is what you get by using the previous formula. A more interesting formula, and not obvious at all, is what happens when you have bending energy, which is one of the interesting limits of nonlinear elasticity. When you have let's say a surface that is can bend, okay, you can this is easy to do, but it cannot do other things, stretching, for instance, shear. The differentiation is this formula here, which I'm going to describe in a second, and it's a little complicated. You see, you have here a Dirichlet form, you have a cubic term involving the mean curvature, and you have the Gauss curvature kappa, the product of the mean curvatures, which is a bad sign, a sign of trouble, if you just leave it like that. The reason why this is the definition, this is the formula, which was, I guess, first computed by Wilmore, and this is the reason why it's called Wilmore energy also in geometry, is like this. So you get formulas like this coming from shape calculus. The shape derivative of a normal in the direction B is this quantity. The shape derivative of the total curvature is this quantity that comes from calculus, and I'm not going into it. The normal derivative of the mean curvature is this quantity. It involves, as you see, the tangential gradient of the normal square. This quantity, the tangential gradient of the normal, is an important operator. It's the shape operator of Weingarten map. It contains all the geometric information of the second fundamental form. In 2 dimensions, it's 2D surfaces, is related to mean and Gauss curvature like this. So then you go through the formula that I just mentioned before, through this formula, okay? Apply these expressions, all right? And you end up, by simply replacing, you end up with this, which is what is written here, except that I didn't invoke the K, the kappa. I left it in terms of the Weingarten map because it's a better way to solve the problem eventually. They are equivalent. But this has a hidden variational structure that is important to exploit. And as you see, if we integrate by parts here, the test function, the V, on the H, then we get a surface Laplacian of H. So this is a 4th order problem, the Laplacian on H, which is a 2nd order operator. It's a 4th order problem on the surface. Okay. Now, about gradient flows. So I show you examples where the shape derivative can be written as G times V, where G is a multiplier of the velocity, which I call shape derivative. Typically, in the example certainly that I'm going to mention later, they are of this form. It's a function times H plus a function. You will see the examples. But then I want to define the concept of gradient flow, that at least at this stage is a way to do numerics. You may want to think of this as a natural or physical process. That might be also true in some examples, but I want to deform an initial configuration into something that will be a minimizer. And I want to do it in a continuous way. I want to define a flow, a descent flow. I already told you what the gradient is. So then I need to talk about this part. In order to do that part, I introduce a scalar product on the surface. This is going to be a Hilbert theory. So B is a scalar product. Think of the L2 norm, okay, if you want to fix ideas. And then I write this in weak form. I multiply by a test function, but I measure this in the metric induced by the inner product, which is left-hand side, and V is the velocity with which I'm moving the domain, which is this dtu. And on the right-hand side, I have minus the gradient, the shape gradient, in the direction W, which is this in weak form. Okay, that's a gradient flow. And it has a property, as you would expect, that if you take W equal to V, okay, then you get that, because this is an inner product, is minus V squared, And so the shape, the derivative of the shape is a negative quantity, so it's decreasing, unless the velocity is 0, in which case we are at the minimizer or a critical point, and we can stop. Okay? So I'm going to write this problem in this form, capital V times V equal minus G, where capital V is a realization of this operator. Okay? Think of the identity, but there will be other options. And here is a sort of an implicit discretization in time. Imagine that I have a configuration which I call xn, that describes a domain, and I want to go to the next configuration, which is close by. I call xn plus 1, and the connection is to a velocity v n plus 1 that I want to compute. Okay? So I know this, I want to compute this. Then I write this discretized variational problem. I want to minimize j in the new configuration, penalizing the distance between the two domains. And the penalization is 1 over 2 tau. Tau is a time step. This idea of minimization is an important idea that goes back to certainly the Georgi, that talk about minimizing movements, and can be formulated in a very abstract sense, even in metric spaces. So here I'm doing it in this geometric setting. So what is the distance between the two domains? Well, the distance between the two domains I'm going to define to be this quantity, tau times v, measured in the new surface. This is the notion of distance. For me, this is the definition, which you can write in terms of b. Okay? So then you plug it in and do the minimization. This is the optimality condition, which you get by minimization, which is a discretization of the previous formula that I wrote in the previous page. Discretization in time. This has the property that it decreases the energy. You can see by simple manipulation, the energy of the new configuration is less or equal than the energy of the current configuration. So it's a good method. At least it decreases the energy. But it has a problem. This is a very non-linear gadget, because I don't know the new surface. Of course, I don't know the new gradient. This is all implicit. I had to compute the new velocity defined on a new surface with a certain inner product that depends on that surface. So this is a very non-linear thing, and in order to solve this, I will need to iterate. So it's very reasonable to do a compromise and treat the geometry explicitly, an idea that has been very influential in this field and goes back to Zuk, as far as I know. It has been used in several other papers following the original paper by Gerd Zuk. So instead of omega n plus 1, which is in the previous transparency almost everywhere, see, instead of having this defined in omega n plus 1, computing in gamma n plus 1, and so on, we are going to do the following compromise. Replace the new domain, which we don't know, but the current domain we know, and all the operators that appear in omega, like the normal, differential operators, and so on, will be replaced by the current, which we know. The gradient is something we can compute. It has the form g times h plus f. The g depends on omega. We are going to take the current value, the same for f. But the curvature, which is a very difficult quantity to compute discretely, we are going to compute implicitly, because it's very stable to do that. Okay, so with these ideas, we write the problem, this problem, in a simplified way. This is very nonlinear. The geometry is the current. This is a mixture, okay, and we are on the current surface. But we compute the curvature that is hidden here and the velocity implicitly. So the equation now, in vector form, becomes something like this, where the operator is explicit, g is explicit, h and v are implicit. Okay? Even though this looks like a very dramatic change, it can be proved under certain assumptions that this is a stable method. And the only constraint in this time step is due to the geometry. You don't want to go too far to mess up the geometry, but there is no stability constraint in terms of CFL. The mean curvature. Actually, I changed the letter from small h to capital H. Capital H is the sum of the principal curvatures. Okay? That's what capital H is. Of course, it has to be computed.
What do you do geometrically here? What exactly is the geometry? Is it in the same All domain.
Yes, well, you are in the old domain, which I call omega n, and this plus another equation, because I had two unknowns here, h and v. I had to provide another equation for h. They will give you the geometry, sort of, built in h, and the velocity. And with the velocity, you simply update the domain. You know the domain, you do the velocity times tau, and gives you the next domain. And with the next domain, you are ready to continue and apply the same technique.
So the n+1 here is the curvature.
In the new, it's an approximation of what you expect the curvature to be in the new configuration. But it's not really the curvature there, because it's not a fully implicit method. Okay? All right. I have two equations. I have two unknowns, v and h, and I have one equation here. I need to provide a second equation, and that comes from an identity that is very important in geometry, which is this. The Laplace-Beltrami of the position is the vector mean curvature, which is an object in the direction of a normal, and the magnitude is the mean curvature. That's a formula that comes from differential geometry and can be used to provide a second equation that relates position and h and complement the previous one. Okay, the idea of using this in numerical analysis again goes back to Zook and has been quite influential. Okay, but you see here I have a vector h and I have a vector x. In the previous, I have a scalar quantities h and v. So one way to do this is to create vector and scalar variables that at the continuous level are related by the normal, but at the discrete level it will be a little bit more complicated. So this is the relation that they have, and here are the equations. Okay, this is the equation for that comes from here. Okay, where I replace h, I replace x by the current x plus tau v. I plug it there. So you have the v here, you have the old x, and you have the new h. The catch is that the Laplace-Beltrami operator is computed in the current surface. Okay, and these are unknowns. This is the relation between vector and scalar curvature. This is the equation that comes from the gradient flow, which I mentioned earlier, involving scalars. And this is the relation between vector and scalar velocity. Okay? And that method, which I call operator splitting, is what's behind what I'm going to show you in a second. Okay. Then you can discretize in space. For instance, using piecewise linear or piecewise quadratic elements, depending on the application. Quadratics are certainly better in many ways, but I will not get into that. And what you see here is a variational formulation of the previous system of 4 equations. I just multiply by test functions and discretize. Everything is now in the discrete spaces, and this leads to a linear algebra system, a big one. It has to be solved. There are results about whether this is a system that is solvable and in which way we can solve it. Okay, so now let me look into the first application, a very standard and important problem, which is the mean curvature flow. So what is that? Well, the mean curvature flow is a gradient flow for the perimeter. So here is the second example in my list before. The J is the perimeter. The shape derivative of this was h. You may remember from before. If you don't remember, I remind you. The shape derivative was h. So this is the gradient flow. The scalar product is L2. This is an L2 gradient flow, equal minus the shape derivative, and that leads to this equation. That's the mean curvature flow. Normal velocity is equal minus the scalar mean curvature on the boundary. There is an energy law that you get by taking W equal V, which is here, and it's a very important relation. This is the one relation that you need to exploit. The very few results that are in the literature for the mean curvature flow, for instance by Zook, Dekelnik, there are several of them, are based on this inequality, which is not measuring Sobolev norms. You see, you have the perimeter here. This is important to take into account. And if you want to look at this in vector form, a formulation that goes back to Zook also, here is the velocity in vector form, is the scalar velocity times the normal. And if you multiply this equation both sides by h, by nu, you get this. This is the scalar, the relation between a scalar and vector curvature. And this is the relation between vector curvature and position, which I mentioned in the previous transparency. If you put it together, remembering that this is the derivative of x with respect to time, you get a heat equation on the surface. And that's what mean curvature flow is. The parametric approach for mean curvature flow is just heat flow on the surface. So the discretization of this is simply like the discretization of heat flow, except that the domain is changing. But the construction of matrices and the solution is the same. It's a little more complicated, but not much more complicated. Because you have here, for instance, the semi-discrete problem, where I discretize in time and not in space. And once you see this, then you discretize this in space. So that's what's behind. That's one approach, a successful approach. A problem of this approach, and the problem of all parametric approaches, is that they are based on differential geometry. And if you have the emergence of a topological change, like pinching or like merging, then there is an issue. You need to do something. The geometers call it surgery. You need to do some computational surgery. I showed yesterday a simulation for the electrowetting where there was a topological change, and we performed geometric surgery in that case using the level set approach. Okay, so the problem with this approach is that it's difficult to handle topological changes, but it's very handy, it's very efficient. And it's certainly the method to use if you have no topological changes. And a big advantage is that the geometry is in your hands. You really know the surface, you can compute on it. A different approach, quite successful, introduced by Osher and Sethian, is the level set approach. In this case, we have a function, let me draw a picture here. We have, say in 3 dimensions, we have a function, let me call it phi of x comma t, and if we look at the zero level set of this function, it can be this. So this here is going to be a discretization, it's going to be the representation of the boundary of our domain. And moving this function, actually not just this zero level set, but all level sets of the function by the same rule leads to the so-called a level set mean curvature equation. So to see what you get is you represent the normal as a gradient divided by mod of the gradient. Of course, that requires that the gradient doesn't vanish. H in terms of the divergence, the velocity in terms of the derivative in time and the mod of the grad, and then the equation v equal minus h, I think I'm missing a minus here, becomes this, or this, if you look at in a slightly different way. There are numerical methods associated with this, several of them. I didn't mention all. But this idea, is a very important idea, has led to the notion of viscosity solution for mean curvature flow, and it has been studied by people like this, Evans, Prack, Chen, Giga, and Goto. This theory is important because it goes beyond singularities. This neck here, in some cases, may get very close, and there may be a pinch, and then there may be a topological change. And that is difficult to describe with geometric means, but it's contained in the viscosity notion. And there are also results about regularizing the flow, where instead of the gradient in the denominator, as I said this morning with TV flow, here you have epsilon square plus the gradient square. And that has been studied by these people.
So you must have an initial state with t0.
Yeah.
Which gives you this boundary.
Yeah, you can think of the sign distance function to your given interface.
It doesn't really matter
No.
what kind of functions you choose.
No.
Okay,
No. The only thing that matters is what happens near the interface. And in fact, that leads to a whole technology of narrow band computations and so on. Because one argument against this method is that it increases the dimension by 1. But on the other hand, the computation is only relevant near the interface. So there are ways to cope with the higher dimension. Several techniques.
So basically, all initial states describe the same evolution.
Yeah.
For that particular.
Yeah.
Years.
Yeah. In fact, this is one of the merits of this theory because there is a unique solution in the viscosity sense. So the flow is well defined. An alternative approach that goes back to Allen and Kahn, which I mentioned this morning, but I want to give it a slightly different perspective now in the context of mean curvature flow, is this equation. This is the equation I wrote this morning, if you may remember, that I talked about exponential blow up of the stability constant in the error estimate. F is the cubic, and I'm assuming zero forcing for simplicity. So it turns out that this equation is a very interesting equation in the limit epsilon going to 0, as it was mentioned also by Benoit Pertam. In the limit of epsilon going to 0, phi goes to a characteristic, and the boundary of the set moves by mean curvature. So basically, with epsilon positive, what you have is an approximation of the curve going by mean curvature by a diffuse interface. The transition of the function phi from +1 to -1 takes place in a narrow region around the interface. And there is convergence. But the convergence can be measured in several ways. You may have a flow, okay, originally, that is smooth. The flow may lead to singularities, there is pinching, for instance, but it may be smooth for a long time, maybe for all time. For as long as the flow is smooth, okay, there are convergence, the error estimates for the approximation of a zero-level set of phi, the relation, the distance, in house of distance between the zero-level set of phi epsilon and the boundary moving by mean curvature. Okay. Well, this is very good news because remember the interface. If this is the interface, the diffuse interface, this is epsilon, and the true interface is somewhere here. This is our gamma of t. But if we know how to start.
The crazy guy.
He couldn't believe it, right?
No.
Oh, I know the guy. He's strange.
He's a host.
Okay, so what I want to say is that this is an interesting result in the sense that the layer here, the thickness of this is epsilon. But the error estimate, if you start correctly, is epsilon squared, which is is 1 power more. Okay, this is very important for numerics. There is convergence in the viscosity sense, and it's convenient, and I wanted to mention this in passing because it has to do with the discussion of the obstacle problem earlier. You can replace this expression here, this cubic, by something else. Instead of a cubic, you can get this double obstacle. So the quartic is something like this. It gets replaced by something like this. Actually, like this. This is and the derivatives, which are the f's, are something like this. This is f, or something like this. Okay, this formulation, so-called double obstacle, precludes the function from going outside the domain -1, 1. And it localizes the problem better. But of course, at the expense of a variational inequality, which I wrote the f in this way. And you have convergence of interfaces also in the smooth regime and past singularities, using the idea of viscosity solutions. What is involved are comparison principles, construction of barriers, non-degeneracy, and asymptotics. I'm not getting into the details. Okay, so here is another example, second example, of surface diffusion. This is an important problem in material science. The equation is written here. Think of the following problem. You have a domain, which is an elastic body, and there is a misfit here on the bottom because the lattice of the solid is different from the lattice spacing of the substrate. And then it has to accommodate to the lattice of the substrate, and that induces a stress. So this is a stress solid, but the top is able to deform plastically. So people in material science have thought about a simple model that incorporates the elastic stress here, which I'm simplifying even further by putting the Laplace instead of the elasticity equation. So the elastic energy would be the gradient of y, where y being the solution. This is an example of y that I mentioned before. And the y will satisfy a simple equation mimicking elasticity with periodic boundary conditions. On the bottom there will be this condition, meaning that there is a stretch of the solid, and on the bottom this that mimics traction free. That would be on top. Okay? This equation, that is a dynamic rearrangement of particles on the bottom, on the top, on the gamma, can be derived using the ideas of gradient flow. You start with an energy like this, which is the Dirichlet integral plus a penalization of the perimeter of the top, and you apply it with y satisfying this equation, and then you apply the techniques that I mentioned earlier. If you do that, you have to do some calculus. You have to find what the equation of the shape derivative of y is. The shape derivative of y is a solution of another problem with certain boundary conditions. This requires some checking, which I'm not doing. Then you end up with this, which is exactly the formula mentioned before. Okay? Here. Except that there is a Laplacian. Okay, so this is the shape derivative. You see the structure, you have an f, you have a g, which is gamma, in this case a constant, times h. So what is the gradient flow? The gradient flow is going to be, let me go back. The gradient flow is a gradient flow for this energy, but using as a scalar product on the surface, the h minus 1 norm. Okay? So then you would get that delta minus 1 of the velocity will be minus g. That's the equation. It's a question of what is the scalar product on the surface that defines the gradient flow. And that leads to this equation. Here. You can view the Laplacian as an inverse Laplacian on the other side, and that induces the scalar product in h minus 1. Okay. So let me show you a couple of results. This is a cylinder. It's actually a prism, 1 by 1 by 8, and it's running by surface diffusion. That means, in the context of what I just said, that this is gone. There is nothing inside, nothing in the bulk. This is purely geometric problem. Okay? There's no y. And I want you to see what happens. So this is the evolution. It's rather slow at the beginning, so it rounds out. The surface, the area is preserved in this flow, but you see there is a tendency of pinching in the middle. It doesn't want to become spherical because it's too long. It's much more convenient energetically to pinch off and do that. And with this parametric approach, we can go all the way until pinching. Let me see if I can. I don't know if I will succeed. I wanted to. Okay, so let me do this. I want to go back a little bit so you see the structure of the pinching and the mesh, which is quite reasonable even until the end. In order to do this, as you can see, there is a need of dual activity, refinement, and so on.
Will it go faster when you get...
Yes, yes. I think that the pinching probably takes place at infinite velocity. Yes, it accelerates dramatically. But the understanding of...
What is this thing trying to do, minimizing what? The surface stress?
No, this is a pure geometric problem. Okay, there is no stress here.
Okay.
Okay, this is just a gradient flow for the perimeter, but the gradient flow is not L2, it's h minus 1. It's an h minus 1 gradient flow for the perimeter. And results about pinching are very few. I mean, there isn't much known about what's going on with this problem. what is the structure of the singularity, you can see numerically that you can expect singularities forming, but what is the structure, what happens is not known. In fact, the problem is not very well understood from the PDE point of view, even before singularities. This is a very open field from the PDE perspective. Numerically, this is a method. There are other competitive methods. This is one of the very few, one of the very first that I've seen. And here, I want to show you what happened with the same problem where there is a bulk effect. Here there is elasticity, and this is an interaction between the surface that is slightly deformed and actually the Laplacian. And I want you to see the effect of stress. This is something the materials people wanted to see because this is what they observe in experiments, in lab experiments. So you see this upper surface is deforming a little bit. The volume is conserved. So it's sort of going down a little bit, accelerating, as you see, creating an indentation that eventually, as you see, goes in and closes. And this type of configurations are observed in experiments. So this is an interesting and simple model that describes that. Of course, you have to do surgery to cut here and continue the simulation. But these sort of insertions in materials are known. They are known from experiments, and they are bad. They want to get rid of this, or at least manipulate it in a way that they know what's happening. Okay.
They appear in molding, no?
Yeah. Yeah. And having these things may be not so good for certain optic properties sometimes that they want to have. Well, here is another example. I'll go very quickly over it. Here you have a domain functional where, let me do this, erase. Say you have a domain, and you have a portion of the domain, which I call D, where this D is where we want our solution to best match a given function Z, match it in the least square sense. Y is a solution of a problem, okay? It's 0 here, this is gamma 2, and somewhere here in the middle, in gamma 1, it has this condition that the normal derivative is equal to 1. Gamma 2 is fixed, and you want to modify gamma 2 in a way that you better match the condition, the given function Z on the top. Okay, this is a problem in shape optimization. Okay, the function Y, as you see here, satisfies an elliptic problem inside, which would be this domain between these two curves. But this is not such a direct problem because here our functional is in the L2 norm, it's not the energy norm. So in order to relate this with the PDE, we need to introduce multipliers, introduce the adjoint variable, do a Lagrangian approach, which I skip altogether. Here is the dual variable, which I call P, satisfies this equation. And after some manipulation, this is the form of the shape derivative. It contains terms like this, tangential gradients of Y, solution of the problem, P, and H times P. P is the solution of this problem. As you see, P here is a function whose Laplacian is chi, the characteristic over the domain D, times Y minus Z. So if you want to approximate this in the mean sense, in the least square sense, you expect Y minus Z to change sign. Okay, that's the best way you can approximate a function. If you are on one side, you can always increase or decrease the function to approximate it better. So you expect Y minus Z to have signs, and so P in general will not have a sign, which means that this function multiplying dH in general will not have a sign. Mean curvature flow is the L2 flow when you have here 1. Here P can have any sign. So this can be forward parabolic if the sign is positive, and it can be backward parabolic if the sign is negative. And this is what happens. This is a problem where we want to evolve an initial ellipse towards this direction. You will see why in a second. Maybe I'll show you the simulation that works. This is an initial ellipse, and it has to move in the center because the correct configuration is a circle. So this part, if it moves by mean curvature, is moving in the direction opposite what mean curvature wants to do, which is to make the domain more convex. This is moving in the right direction. So one part is forward parabolic, the other is backward parabolic. And if you do an L2 flow, which would be the natural thing for the mean curvature flow, this part is unstable and that part is stable. And this is one of the messages that I wanted to give of the danger of discretizing first and minimizing next. You can always, when you have a minimization problem, you can always try to formulate, you can always try to discretize it and use your favorite tool from the shelf, minimization tool. A minimization tool is going to lead to some kind of flow, a numeric flow, some kind of continuation, numerical continuation that may lead to this. In order to avoid this, you need to understand the structure of the problem to come up with a regularization of this. So it's better not to discretize, it's better to formulate the continuation, the deformation at the continuous level, at the PD level, and understanding the PDE properties, discretize at the end. Okay? And this is what happens if you use what I call a weighted H1 flow. So instead of using the L2 flow, you use a weight for the H1 norm, and that regularizes this part. It's like introducing for a fourth order problem a damping that has that effect, the geometric effect. Okay, now very quickly, a next application about membranes. Maybe let me mention the whole thing very quickly. Okay, so as I said at the very beginning, this is the Wilmore energy. This is the derivative, the shape derivative of the Wilmore energy. This was the third example earlier. In the applications of membranes, it's typical to have an area constraint because the membranes don't stretch very much. First approximation, you want an area constraint that is enforced via a multiplier, and a volume constraint. Perhaps there is a fluid inside and you want to mimic that, not change of volume or area. So the functional arm becomes this, with these two additional terms. This is the derivatives of these two quantities. Okay? And then you can create a gradient flow for that. Before, I want to mention a method that gets around this curvature, this Gauss curvature. And this is the form of the method. You see it involves computing Dirichlet forms. Actually, this is well, I will not go through the derivation. Let me just say that the final method that you had to do, you had to imply that we implemented has to do with the Dirichlet form, a modification of the Dirichlet form through a projection, and divergence. So it's all first order, as you see. Nothing has to do with second order derivatives. It's easy to implement in a finite element context. And it gets around the fact that here there is an object that is fully nonlinear. Related methods are written here, and particularly I want to mention this, which is quite efficient, by Barrett, Garke, and Nürnberg. And you can do this for fluids. So now you can have a Navier-Stokes equation governing the fluid inside the membrane, and the interaction with the membrane is through an equilibrium of forces. This is the membrane, this is the traction of the fluid, and it's equilibrated by this force produced by the bending of the membrane. Okay, so this is a problem that is Navier-Stokes inside, here written in Lagrangian form, coupled with the membrane, and it's a fourth order problem on the boundary. Okay, here is again the form of the shape derivative. And I wanted to show you a simulation that compares the two. So this is the initial configuration. It's a cross section. Think of an ellipsoid, okay, like a flat ellipsoid. In red, you have the fluid. There's a fluid inside, and in white, you have just the geometric object without fluid. The fluid is sort of replaced by assuming area and volume constraint. And this is the evolution. Perhaps it's more insightful to see what happened with the cross-section. You see the fluid expands in the middle, and then it bows all the way to the boundary and creates a much thinner neck. Okay? So in this simulation, that as you see incorporates effect of inertia, the fluid has a very different dynamics than the geometric flow. In applications to membranes, let me skip this. When with physical parameters that have to do with membrane cell membranes, the behavior is not that different. It's different, but the effect of inertia is much less pronounced. The red is again the fluid, the yellow is the geometric. Okay? All right. How am I doing with time? 10 minutes? Okay. So let me first, this is something I'm going to do very quick, it's very recent, and it's about coupling surfaces and director fields. And the idea comes from dealing with surfactants. So now you have a surface and a director field that represents maybe a surfactant acting on the surface, or it may be the orientation of the molecules on the surface, the bilipids, relative to the normal. The normal I always call nu, and this n is a director field, it's length 1, but it may not be aligned. The question is how to couple the director field and the membrane. And the coupling is like this, is the simplest possible. You have the bending energy, you have a Frank term that sort of is a regularizing term for the gradient for n, typical of liquid crystal theory, and then an interaction. Okay, and this interaction is what I want to tell you, to describe to you a little bit. Okay, the interaction eventually leads to the following system, where instead of the curvature, this curvature, which is the divergence of the normal, you get a correction. A correction that has to do with the divergence of the director field. It's like an spontaneous curvature coming into the problem, but not given ahead of time. Is a solution, is the divergence of the director field, plus the Frank term, plus the Lagrange multiplier implementation of the length constraint, plus an implementation of the angle between n and nu, if you want to do that. And now you want to compute the shape derivative of this. And believe me, if I didn't know shape calculus, I wouldn't have done this. The result is quite a mess. Here it is. It's not important to see it. You have to do it several times to get it right. In red, you distinguish terms that have to do with the previous transparency.
Remember this?
Of course not. I just want to illustrate that there is a merit of knowing the shape differential calculus, because you can go through this. This is what the shape derivative is. In red is what has to do with the previous case, the bending energy. The derivative for n is much easier, as you see it here, and then you can create a gradient flow, very much in the spirit what I described earlier. Here you have simulations without surfactant, with surfactant. So the surfactant decelerates the behavior, and instead of having a concave form very pronounced, it's much less pronounced. And here you have, for instance, the effect of degree plus 1 defects on the poles. These are on the north and south pole, and you see the creation of a singularity, cone type singularity, on both the north and the south pole. You see the formation. Of course, they are not quite singular, but these are the type of singularities that you would expect if you have defects plus 1. Here is what happens if you have deflect plus 1, but one is going inside and one is going outside. You get like an apple type behavior, you see. And of course, for this type of problems, we know basically from the mathematics standpoint, analytic standpoint, we know very little. Only in the case of graphs, we have some understanding. This is all completely open. And here is a problem where you have a sphere, and on the poles we put defects of degree -1. These are saddle points. Okay, as you can tell, these are saddle points. The evolution leads to the formation of 4 singular points around the equator, as you see here. This is the equator of degree +1. And it has to do with the structure of the sphere and the theorems about the topology of the sphere and the number of singularities that you can have. Okay. Okay, so let me say only a couple of words. This is, as I said, a tour on a list of problems without many details. I wanted to bring this as a conclusion because it links everything to some extent. This is an application of phase field models, not quite Allen-Cahn, more of the type of Cahn-Hillier, in order to describe two-phase flows. So here is the equation for the phase field that describes the two phases of the flow. It's Cahn-Hillier type. You see here there is a mu, which is a chemical potential that in turn depends on the Laplacian of phi, of the phase variable, and the cubic nonlinearity. So altogether, this is a fourth order problem. U is the velocity of the fluid, which is governed by Navier-Stokes. But in this problem, there is much more than just a fluid with two phases. There is an electric field, which is induced by a potential V. This is the electric permittivity, and there is a charge. And so this is a complete system that governs the evolution of a drop that is sensitive to the electric field. And by playing with the potential, we can deform the drop and manipulate it, as I mentioned in the second lecture. But this is a more complete description of it. So to conclude, I want to illustrate with this example. So let me see if I can move it so you can see better. Okay, so here is the drop again. You see the diffuse interface. This is the original interface in dotted lines. These are regions where the potential changes from small to big. Here the potential is big. Here the potential is big. Here the potential is small. So these are iso lines of a potential, isopotential lines. You see that the drop wants to go where the potential is larger, and that eventually leads to a pinching here, which is rather slow until it touches the boundary and then it moves. So this is a combination of modeling and numerics. The modeling is of two-phase fluids. Okay, there are two phases, and in order to describe that in the context of diffuse interfaces, what comes handy is the Cahn-Hillier equation. So this is a Cahn-Hillier Navier-Stokes type of system plus electric field plus charges. So I thought this would be an interesting example for you to see, for which we have very partial understanding of the analysis, both the PD level and the numerical level. So thank you.
In all your pictures, there seems to be a waiting time. Well, not really waiting time, but still it takes some time before it starts going in.
Yes.
The middle. What is it?
Well, I don't know. I mean, this has to do with the dynamics. I don't really know why. This is what comes from the simulation. The pinching is fast. This is always the case.
Somehow, if you're an almost infinite cylinder, rounded up, it would take, this guy would never go in.
No. No, why?
That's what the picture says almost.
No.
If you make it larger and larger.
No, well, no, it's not. I don't see why it has to do with the length. No, I don't know. Certainly not in this example, but for the surface diffusion example that I mentioned, this
2D. Okay.
I don't know. I mean, maybe you have a different insight from mine. I don't know. I don't see. Certainly, in examples that I've seen different from this surface diffusion, you can have a long cylinder. If you have a long cylinder, then you will have more pinching points. Okay, not just one. For instance, I didn't show the simulation, but I can show it to you. If the cylinder is 16 by 1 by 1, you have 2 pinching points. If you make it even longer, you may have more. So what is the dynamics and how is the minimization of the energy taking place is not clear. It depends on the geometry. But I don't know about this particular example. We didn't try longer configurations.
When pinching happened, it's immediately the contact angle, that is the angle between the fixed and the free boundary.
Yeah.
It seems it's 90 degrees.
Yes.
It's a constraint in your equations, or it's
No, it comes naturally. It's built in. There is an equation which I didn't write because it's quite messy. That had to do with the dynamic contact angle. I can show you. This was already complicated. Now this is a big system with many equations, two of which I didn't show: the electric equation for the electric potential and for the charge. And then there are boundary conditions that have to do with contact line pinning, with contact line. Okay, there is no pinning in this formulation. You can incorporate pinning, but it's not in this formulation.
Okay, let's thank Ricardo for
Thank you.
a very nice talk. Of course.